Hey guys, this is Srini, and in this video let's continue our discussion about UNet that we have started in the last tutorial. Well, in the last tutorial we segmented mitochondria. In fact, we did a great job segmenting mitochondria, but I highlighted one of the potential issues, which is if you have some of these objects very close together, there is a good chance that this and these two segmented objects touch each other. So when you do any object measurements, then your measurements would be not reflecting the true case that's captured in your images. So one of the tricks that we typically do is, or one of the approaches that we take, is performing instant segmentation. So you probably heard about mask or CNN, for example, for instant segmentation, which is okay for like humans and cats and dogs, but for most scientific images, especially if you have images like these, like light or electron microscope images, biosciences, or even geosciences and material sciences, these type of images, scientific images, I truly believe that performing a unit-based semantic segmentation and cleaning it up using watershed, or separating these objects using watershed, is equivalent, if not better, than the other approach when it comes to instant segmentation. Okay, so our goal in this video is to go ahead and build on what we have already done in the last video, meaning let's take the trained model that we have used in the last video. I definitely recommend you to go back, watch that if you haven't, and continue that, right? I mean, let's go ahead and segment these and identify the problem and go ahead and separate these objects and try to report the object parameters. Okay, so that's the case. Now, what is watershed? In case you don't know, I have covered this as part of my, I believe, video number 33 when I talked about grain size analysis. And I did, I believe, quite a good introduction to watershed. But here is quickly the summary of watershed, right? So if you just look at your image as intensities, if you just look at this image as a bunch of intensities, right? I have high intensity, low intensity, high intensity, low intensity, right? Just take a line scan here, or just a cross section right there, and look at the intensity. It would look something like this. Okay, you have high intensity and even higher intensity, and so on. Our goal is to identify the border between these two, right? So if think of this as a valley and hills, right? Or a watershed. So you start filling water right here and then keep filling it until this touches the other one, right? So here at this level, this water touches this water, which means wherever that happens, that's your boundary. Okay, and you're separating that, right? So that's your boundary right there, and keep filling it. And then at some point, you'll have another boundary right here and draw a boundary right there. So basically, if I go back here, if I start somewhere in the middle right here of this grain, somewhere in the middle of this grain or mitochondria, and then keep expanding, okay, keep expanding. At some point, these two touch, and that is my border. Now, the point here is you don't start too small. Then your shape would be all circular when you keep expanding, right? You don't start, so you have to just start, basically the idea here is to mark most of my mitochondria as, oh, I'm sure this is mitochondria. And most of the background as, I'm sure this is my background. And define an area that you're not sure of. Hey, this is the ambiguous area where I need your help, watershed, and then separate this two, right? So here, define this as, yeah, I know this is definitely a valley. I know this is definitely a valley. I know this is definitely a peak, but I don't know where the separation is between these two. In a way, that's what watershed does, okay? So now let's jump into the code and just get started. And just to remind you, we have 256 by 256 images, patches, and corresponding masks. And we trained our model on these. And what model? We defined our model in a separate file here, and we imported this. And this is our standard unit. Okay, just Google search for unit and maybe Keras. You'll find a whole bunch of these Keras code, or Python code. Of course, you can copy mine. And then we have used our simple unit model to train on these images and masks, and we saved it, and I saved it as the file name mitochondria 50 plus 100 epochs. Well, I trained it for initial 50, and then I was curious what happens if I do an additional 100. Nothing much happened, but this is what I saved. So now let's jump into the code for today, or for this video. What is it? Well, let's start with a clean slate, and let's go ahead and load our libraries that we need. And most of these you should already know. And the first line is basically we are loading the model, right? I mean this model. And we are going to normalize our data, and OS, CV2, and all of these you should definitely know. And the next thing is just importing the model. Okay, and for that, let's go ahead and define our image height, width, and number of channels. And let's go ahead and get our model. Okay, again, remember our model takes 3 parameters: image height, width, and channels. That's exactly why we defined it here. Let's go ahead and import it. Well, we haven't imported, we just defined that, hey, when I type get model, go ahead and get that model. So let's assign that to our model, and we are all there. Now you see this is our model. Again, we looked at it in the last video, so no point in looking at it. Now that we have this, I can go ahead and load the weights, okay? And it'll tell me, hey, you're trying to load weights for a model that's not the same architecture as what you have trained on. But obviously, I know that this is what we, I have trained on, so it should be fine. Okay, so now I loaded the weights. So initially, you loaded the bare model. Now you're assigning weights to each of these weights, or 1.9 million parameters, I think, that we trained. And now I'm set to predict. That's it. This is, once you have a trained model, just implementing is so simple, right? I mean, you just take the trained model, load it, and then go ahead and load your images. Okay, so let's load one of the test images and pre-process it. How did we train our model? Well, we basically expanded the dimensions, and we normalized the pixel values, and and then I mean, this is basically the pre-processing that we have done with our initial data. So I'm doing exactly the same thing. Okay, now I'm ready to go ahead and predict it. How do you predict? Model.predict, right? So that's exactly what we're doing here. Model.predict on my test image input. And my test image input has a dimensions of 1 by 256 by 256 by 1, because I loaded only 1 image. If I loaded 10 images, that would be 10. Very simple stuff, but it's worth repeating. Okay, so once you are done predicting, okay, go ahead and threshold it by showing me all the pixels above value of 0.05. Let's actually run this line so you can see exactly what we mean. Okay, and so now that it's done predicting, let's go ahead and plot. Okay, so this is exactly the stuff that we have done in the last video. So there you go. You see how this is touching, and that's the reason I changed this to 0.05. In fact, if I put 0.5, our model is doing such an amazing job in separating these two. There is nothing to show in this video if there is nothing touching. That's exactly why I'm changing this to 0.05. So I intentionally make this entire thing a bit not as good. And now you see these two are touching. So if I do object analysis, then these two would be considered to be one single object. Okay, now I just need to do, in fact, one thing to note here, this model is doing such an amazing job. Even if I put my threshold as 0.05 probability, okay, 0.05, the image still looks very nice and clean. If this is random forest, this would be completely crappy. Okay, and I've done that experiment already. Okay, so let's do this. So now we have our segmented image. Let's go ahead and save it to the disk so we can refer to it later. And here I'm importing it again. I'm saving it and importing it again. Okay, now if you look at my image, I'm reading this as color, because later on when I overlay it, I believe it requires a color image, okay, or 3-channel image. That's exactly why I'm doing this. But my gray image is basically, let's take the 0th channel. Okay, so this is my gray image. Again, plt.imshow I really don't want to confuse you guys. So let's go ahead and plot at every step. Okay, I'm going to share the code anyhow, but there you go. So we, again, if you change this to CMap equals to GRAY, it should look decent. Okay, there you go. Okay, just to prove that, okay, we got our original image back after saving it and reading it as 3-channel and extracting only the 0-channel. No surprises there. Okay, now let's go ahead and threshold this image. Okay, right now it may not be. In this case, it looks like it's threshold, but let's go ahead and say, hey, perform an OTSU thresholding. And again, I've done many videos on this. So this is basically OpenCV thresholding, right? So this is binary thresholding. So let's go ahead and do this. And if I plot, let's leave that statement. And if we just go ahead and plot my thresholded image, it should look pretty much the same. Yeah, there you go. Okay, now what? Now let's define a kernel and performing some opening operation. I'm showing all of these even though my image doesn't need this. I'm pretty sure most images require this. Okay, that's exactly why I'm covering this. So here what I'm trying to do is I'm actually doing morphological opening, meaning like image processing operation. So if I have like a pixel here, a pixel there, a pixel here, you know, that are like that it thinks are mitochondria pixels, this is a great way of cleaning it up. Okay, again, every time you do any of these, go ahead and have a quick look at it, and let's do that. Let's do the same to see if it makes any difference. You see, slightly, not much difference in this case. Okay, so now let's I commented out a few other steps right here, and I mean a lot of notes, and I commented a couple of steps like clear border, for example. Clear border removes all the objects that touches the border. In this case, if I do that, I would end up with nothing. Okay, so I'm not going to do that. But if you have tiny objects spread all over the image, and if you want accurate object analysis, then you may want to remove these border objects. Okay, so I'll leave that line over there. But now let's go ahead and find our sure background. Remember, we talked about sure background. Hey, I'm sure this is mitochondria. I'm sure this is background, and I am not sure what's in between, right? So that's exactly what we are trying to define. So one trick to do that is just go ahead and dilate. So let's go ahead and plot this so you can see exactly what's happening. Again, most of the time I'm using erode, dilate, opening and closing operation. Opening is erosion followed by dilation, or dilation followed by erosion, one of these operations, right? So let's go ahead and plot our sure background. You see, it's saying that, hey, this is my all the black area is my sure background. Okay, I dilated my actual mitochondria by a little bit, showing that, okay, everything else I'm almost 100% confident this is my sure background. And my sure foreground will be very similar, but how do you define your sure foreground, right? How do you define the center of mitochondria? If I go back to this image, how do you define this? If you only define like the central few pixels, if your mitochondria is elongated, then how do you define this shape? So for that, we have something called distance transform. So I'm going to, it's actually looking at the distance, and it kind of, it converts, you know, it maps that distance. Then we can say, hey, set a threshold on the distance transform. Okay. Again, if this concept is new to you, go ahead and I include the link here. Educate yourself on what distance transform is. Before you do anything in deep learning, I definitely recommend you to learn as much as you can about traditional image processing. Yeah, because traditional image processing solves 95% of your life problems, well, image processing problems, and the remaining 5% probably you need machine learning. Okay, so let's do distance transform here, and based on the distance transform image, I'm going to threshold some of the pixels. Okay, so now I have a distance transformed map. Okay, for each of these, like for this image, I'm segmenting that map. Okay, I'm thresholding that map basically, so I get the sure foreground. So let's go ahead and do this so you understand exactly what we are trying to see. And for that, I'm actually putting a threshold value of 0.25 multiplied by the maximum of my distance transform, right? So if the max here is whatever that value is, I'm doing 25% of that. This is very important. We'll see why. Because then you can get weird shapes if you don't do this in a minimal way. Okay, so let's go ahead and do sure foreground map. Okay, sure foreground. So there you go. So I'm kind of defining it, but it's like erosion. Okay, a few pixels. I'm defining the shape. This is where I'm telling that, hey, I know for sure this is my mitochondria for sure. Okay, that's exactly what we are doing. Now, the reason why I said you should be a bit careful about this value is, let's go ahead and change that to 0.5 and run this again. You see how I'm like eroding this, or making this too small, right? Making it too small means now when you actually try to figure out where the boundary is between these two, then the shape would be very weird of this mitochondria, and you lose all the actual shape. So you got to be a bit careful. Let's go down to 0.1 and see what happens. And sorry for spending too much time here, but this is very important for you to understand. Now I changed this to 0.1. You see how that connectivity is still there. When I do that, that means if I proceed, this is not going to help. Okay, and maybe 0.15 will do that. So I usually test this on a few images, and then I make a decision. So 0.25 is probably okay, right there, or 0.2 is probably okay. I don't think I plotted with 0.15. Let's do that. 0.15 is also okay. Yeah, so for now, let's go ahead and leave it to 0.2. I think now you know exactly what's going on. Okay, we define sure background, we define sure foreground. What is the area where we don't know what's going on? It's just one minus the other, right? This is the area where we don't know anything. So that's exactly what we're trying to do here. Sure foreground, I'm changing this to 8-bit values. And my unknown is basically sure background minus sure foreground, right? Background minus foreground, these overlap pixels is my unknown area. So let's go ahead and do the math and plot unknown. Okay, so this, you see, these are the areas where I need help filling, where I need watershed's help. So I hope this makes sense. There is a, I wasn't planning on giving a watershed again, how should I say, watershed tutorial, but if you don't come from that background, this can be a very useful lesson. Okay, now what are we doing? This part is, now we are creating markers and labels. This is traditional image processing again, right? So now let's actually set up our markers. So if you go up here, so what do we have? Our markers are 256 by 256. Can we plot it? Okay, let's go ahead and look at our plot, and there you go. So these are all our markers, and again, all it's doing is connected components, right? I mean, it's basically saying, hey, this is not connected, this is not connected to anything, this is not connected, this is not connected. So it actually assigns a value of, I don't know, 1, 2, 3, 4 to each of these objects. So all we are trying to do is connected component analysis here, or connected components, and separating these markers. Now, if you just look at this markers right there, if I open this, you see it's got a value of 0 in the background, and if I go here's value of 1, 2, 3, 4, right? So object number 1 probably is all the way up here. So let's do that again. Something that's very important for you to realize. Okay, so you see how this object has a value of 1, background has a value of 0, and the next one value of 2, 3. So let's go back to our plots. Value of 0, background pixels 1, 2, 3, and 4, right? Now, later on, when we actually do this watershed, if values of 0 are going to be a bit troublesome. So what we'll do is bump everything by value of 10, meaning I want all my background pixels to have a value of 10, and all of these pixels to have a value of whatever, 1, right? 11, 12, 13, and 14. That's pretty much what we are trying to do. Okay. So again, the reason why we are doing this is all values of 0, watershed thinks that this is an area it has to work. So our sure background is the only one that needs to be, our unknown is the only region that needs to have a pixel value of 0, and everything should have non-zero pixel values. So watershed only looks at, okay, here are pixel values 0, let me work right there using other information. Yeah, that's exactly the reason why we are doing this. Again, please don't be confused. Practice this a couple of times. So all of our markers, we are adding 10 to all of our markers, but we have to convert our our boundary areas, right? These areas, we have to convert these areas, the pixel values to 0. So Watershed understands how to work with this. Okay, so for that, how do we do it? Markers wherever my unknown equals to 255, right? Remember our unknown, this is our unknown image. So background is 0, this is 255. So all we are trying to do is wherever my unknown is 255, go to my markers and change the value to 0. Okay, so let's go ahead and do this. And if I plot it, you'll see what we mean. So there you go. So we have, I mean, you can change the color map to something else, but in the background we have, in fact, let's go ahead and change this to gray. Maybe it makes a bit more sense if it is in gray. Okay, so the background, we have a value of what? 10, because we added 0 plus 10. This is 11, this is 12, 13, and 14, and our areas where we need help with water from Watershed, these are all 0. Okay, so far so good. And now let's go ahead and do our Watershed. Okay, for that I'm going to supply my original image and the markers where it is actually trying to work. So this is our new markers, and let's go ahead, and if you look at our markers right there, I think it does make sense to plot this just one more time. Okay, let's plot it, and there you go. It's already defined the boundary. You see, each object is separated. Okay, now it's just a matter of processing. So let's go ahead and, sorry, let me do that. Okay, so by the way, when it defines these markers, if I actually go to my markers, hopefully we'll find -1. You see -1s right there. So wherever you see -1, yeah, you see this -1s, that's the border that it defined. So Watershed, what it returns is the border pixel values as -1. So let's convert that to some color so we can kind of see that on our final image. So I'm going to change the values of -1 to red, green, and blue, right? So this is yellow when you combine these two. So my markers are in yellow, and now let's convert this labels to RGB and markers. Okay, yeah, you'll see the output. This is pretty cool. So once we are done with this, let's go ahead and plot it in OpenCV. And there you go. So what it did is labels to RGB. Obviously, as you can see, these are all my colored grains. This is exactly what labels to RGB does. Okay, I hope things are clear now. You see, these two used to be one entity. Now they are separated into two objects, object 1, object 2, 3, and 4. So we have 4 objects in this image. Okay, so this is like instant segmentation. We did initial semantic segmentation. Now with Watershed, we separated areas that were close by, and then now we have well separated objects. So this is our instant segmentation. Once you have this, then getting your object properties is very easy. In scikit-image, you can import measure and region props table. You can also do individual region props, but region props table, especially if you have the latest scikit-image, they included this. This directly gives you a table of all the properties that you want listed. So let's go ahead and do that and capture that into a pandas data frame and go ahead and print it. So there you go. So I have I should have 4 objects. Okay, I see the issue here. You see how label number 0, this seems to be the background. It's actually identifying this as another object, but the true objects here I may have made, I'll have to go back and check, but this is nothing. This is easy because I know my objects have a diameter of some specific range, and if something is 256, then that is too big, right? I can actually filter these out later on in my CSV file or pandas if I'm doing in pandas. Okay, so we have done this for one image, but you probably have hundreds or thousands of images, so you probably know how to do it. But I'm going to share another file with you, another Python file, so you don't have to write it yourself, which is putting all of this stuff that we just did into a function and applying it to multiple images. That's exactly what I've done here. Okay, I hope you appreciate the lengths I go to make sure you don't waste your time doing things that I've already done. Okay, please do something more and share it with others. So I'm exactly the same thing. Is this the one? No, sorry. Here, I put everything into a function and I called it process images. Exactly the same. We read the image, we segment the image, and then we threshold this image, everything, all the operations we just did. You see, you do the distance transform right there, and you perform all of these actions. And what do we have finally? Once you define everything in this function, it's returning three things. It's returning the actual data frame itself, which is our measurements, and it's returning the segmented image, and it's returning the processed image, which is object separated. Okay, and now I just need to call this function. It's very easy, right? So this is my path where all the images are, data, test images. So these are all the images that I would like to segment. And for file in this path, in that path, go ahead and read the image and process the images, right? Process images is this function, and it returns three things, as you know: results table, segmented image, and processed image. And then to the results table, it's a pandas data frame, add a column called image number and add the number for that image. So I just want to say image number 1, image number 2. Of course, you can also add the image name if you want, right? You can also do all kinds of fancy stuff and save my images into segmented and processed subfolders with an extension of original image name plus underscore segmented underscore processed. That's it. So I'll share this, but let's go ahead and run this. It's fun to have a look at this. This should be pretty fast. There you go. Each image is being processed, and let's go to, this is my test images. Let's go to our, where did I say, results, segmented, and here is our segmented. You see, nicely separated, each of these. And let's go to our processed. There you go. Very nicely processed, as you can see. Nicely separated and processed. And did I save the results? Yeah, to measurements.csv. If I go to results, measurements.csv, there you go, from each of these, including the image number 1, 2, 3, 4, and so on. Okay, so again, one of those long videos, but I hope you find this to be very informative. And please like this video if you like it. Okay, do something to these videos so at least I get some hits to my channel. And definitely I request you to subscribe to this. And in the next video, let's actually see how we can actually take this trained model that we have trained on 256 by 256 images and apply that to a larger image. Maybe I have 1K by 1K or 2K by 2K, right? How do we apply this to a larger image? I'll show you a way that you shouldn't be doing, and then I'll show you a way that you should be doing. So please stay tuned and subscribe to this channel. Thank you very much.